Hello everyone, my name is Evan Downing and I'm a PhD student from Georgia Tech studying under Dr. Wenke Lee. Today I'm going to present my work on discovering malicious functionalities in binaries. I will introduce a tool that I along with my co-authors developed called DeepReflect, which identifies the malicious functionalities in malware binaries. To motivate our tool, let us assume Molly is a malware analyst. Her job is to reverse engineer a malware sample to determine what it does. This information is used to improve her company's malware detection software, for example by creating signatures, behavioral rule sets, writing reports, etc. First, Molly receives a suspected malware binary. She queries VirusTotal, but the sample is currently unknown to antivirus companies. Next, she executes the sample in a sandbox to determine if any malicious behaviors can be observed. Unfortunately, the malware employs anti-analysis logic, and she is unable to coax the malware into executing. Because of this, she must statically reverse engineer the sample, but there are several hundred functions to look through. She goes on to search for key API calls, strings, and examines the binaries functions one by one, but this workflow becomes tedious for her over time. Normally, analysts can spend 1 to 2 weeks doing this for each malware sample they are given. Therefore, analysts need to quickly identify and label malicious functionalities within the malware. However, it is infeasible to obtain a labeled dataset of malware functions at this current time. Thus, we aim to identify these regions via unsupervised learning. Once we have identified the regions, we may still want to classify the behaviors, but doing so for all regions is time-consuming. To minimize the labeling effort, we utilize semi-supervised approach, which requires an analyst to only label a few regions. Work on malware classification and detection via machine learning has existed for more than 15 years. However, these solutions do not identify individual behaviors, but rather the whole sample as a malware or malware category. In 2020, FireEye released a tool called Kappa, which uses rule sets made up of specific instructions, API calls, and strings to identify malicious capabilities at the basic block and function level. However, these rules must be created by hand and can easily be evaded by API and string obfuscation techniques. There are two main challenges with building a tool to address these problems. First, it needs to be able to distinguish between benign and malicious behaviors. To address this, we utilize an autoencoder to locate malicious functionalities in binaries. Second, it needs to understand the semantics of the identified malicious behavior. To address this, we used a semi-supervised clustering which classifies the identified functions. These clusters will require only a few labels obtained from the analyst's daily workflow. So now let me introduce our solution. DeepReflect takes an unpacked malware sample as input. Next, it extracts basic block features to then pass to a pre-trained autoencoder. The autoencoder identifies various regions of interest, also called ROI. Next, it clusters these extracted ROIs with ROIs from other malware samples. The analyst then labels each of these clusters by examining a few of the functions in each cluster. This in turn propagates these labels to other similar functions within those clusters. Next, I will briefly introduce our model's features. We chose our features based on attributed control flow graph, or ACFG features, which have been used in prior works for bug finding. We modified them for the purpose of identifying malicious functions using features from other prior works, such as API call categories. We note that a benefit of our features is that they don't focus solely on API calls or even strings. Therefore, if a binary is hiding these types of data, our model should still be able to compensate for this fact by focusing on the instruction and structure-based features. To construct our benign dataset, we collected 60,000 benign portable executable, also called PE, binaries from CNET. After unpacking and deduplicating these binaries, we obtained 23,000 benign samples, filtering out possible malicious samples by querying VirusTotal. It was important to have a large benign dataset with diverse behaviors. If not, any behavior left out would be considered anomalous by our model. For example, if applications which implement network-related behaviors were left out of the benign dataset, then any network behaviors would be considered malicious by our model, which is of course not always the case. To construct our malware dataset, we collected 64,000 malware PE binaries from VirusTotal. After unpacking and deduplicating these binaries, we obtained 36,000 malware samples made up of over 1,000 families and 3,000 singletons. We compiled 3 different Windows malware from source code consisting of Arbot, Pegasus, and Carbonok to evaluate as ground truth. We selected these samples based on their age and diversity of behaviors. We then selected and identified and labeled the malicious functions in each of these samples to create our ground truth dataset. To compare our autoencoder, we trained another deep learning model on classifying the malware families. Using SHAP, an explanation framework, we use it to highlight regions of interest, similar to how the autoencoder does. We also compared to Kappa, a tool which looks for key instructions, strings, and API calls to label basic block and function behaviors. Finally, we compared our autoencoder to function SimSearch, a function similarity tool created by Google Project Zero. Training it on our benign dataset, we looked for functions in malware which did not match any function in the benign dataset, similar to how our autoencoder works. Graphing the ROC curves, our tool, shown in blue, outperforms our baseline deep learning model, Kappa, and function SimSearch. On average, DeepReflect achieved an AUC value of 80%. After identifying the malicious functions, our tool needs to present them in a meaningful way to the analyst. Using a threshold of 5% false positive rate, we extracted functions from 25,000 malware samples to cluster. This is less than the original 36,000 samples because some of the samples either didn't finish extracting features or had no ROIs detected above the selected threshold. We had 5 malware analysts label these functions via descriptions by the MITRE ATT&CK framework. Of those functions, roughly 60% were malicious and 40% were benign. For more on how these functions were selected and what types of functions were identified, please see our paper for details. We also had an analyst cluster the functions by hand. Their clusters matched almost 90% of what our clustering results outputted. Therefore, we conclude that DeepReflect can identify malicious functionalities and group them together, and reliably group them together. Next, we wanted to see how much of the malware's functions were identified by DeepReflect using the same threshold of 5% false positive rate. Here, we graph the percentage of functions highlighted in each binary. For most samples, it reduces the search space for functions by 90%. Depending on the complexity of those functions, this can reduce the analyst's effort significantly. You'll notice that a large blip on the right-hand side of the graph, that is, 100% of those binaries functions were highlighted. This is due to those samples being very small, composed of roughly 10 functions total. These samples were simple droppers where every function contains behaviors describable by MITRE, and crucial to the malware's singular task of dropping and executing files on the victim's host. Besides this, each malware binary had roughly 660 functions on average. In addition, the ones highlighted by DeepReflect were larger than those that weren't, indicating that these functions may be more complex to analyze, and thus an analyst would benefit from its assumed label from clustering. Therefore, we conclude that DeepReflect can reduce the number of functions the analyst has to examine in order to identify those which are malicious. Next, we wanted to see what kind of insights we could derive from our clustering results. First, we noticed that many different malware families shared the same functions, such as specific anti-debugging behavior, parsing the command line for arguments, decoding and decryption routines, etc. We also note that no matter which family or which function address in the behavior was located, we were able to manually verify they got put into the same cluster. We also noticed that at least one singleton sample was contained in each cluster. This can help the analyst by labeling and associating those uncategorized samples with those in that same cluster. Finally, we saw that while novel malware families formed only a few new clusters, most of the tens of functions highlighted existed in old clusters, that is, could have already been labeled in the past. Therefore, we conclude that DeepReflect can yield interesting insights into what categorizes a malware family at the function level while also helping the analyst categorize novel malware samples. Finally, we wanted to evaluate how robust our tool was to being attacked. We used OLLVM, a well-known control flow obfuscation tool that implements obfuscations like control flow flattening, instruction substitution, and bogus control flow insertion. Using these techniques in combination, we found that there were only a few new clusters created of these obfuscations. However, most of the clustering results were unchanged, meaning that DeepReflect was still able to identify the same functions and produce the same clusters. We also attempted to perform a mimicry-like attack where we added benign code which was similar in behavior to the malicious code, for example, specific network communications. However, we were still unable to evade our system. And whilst we were unable to evade our system, we are confident that DeepReflect can be evaded by a motivated adversary. However, the attacker's task is difficult due to the features they'd have to modify whilst preserving the malware's functionality. Therefore, we conclude that DeepReflect is robust to common obfuscations and attacks. DeepReflect, like any security solution, has limitations. First, although we were not able to successfully evade our model, we are still confident that it can be evaded by advanced control flow obfuscation techniques. Second, since it relies on machine learning, it is susceptible to adversarial attacks. However, although not evaluated, plenty of state-of-the-art solutions exist, for example, distillation, adversarial retraining, etc., to defend against adversarial machine learning attacks. DeepReflect relies heavily on training dataset quality. If the diversity of the behaviors is not large enough, then the model's false positive rate will increase. This is why we took the time to construct our benign dataset such that it included many different types of categories of software, for example, browsers, drivers, video applications, etc. In addition, DeepReflect relies on human experts to label clusters. We experienced this limitation firsthand when we initially missed some remote desktop protocol implementation in malware, causing our ground truth results to assume it was benign behavior. Thus, we feel DeepReflect is a collaborative tool to be used by lots of analysts together, and can be used to train inexperienced analysts on what different malicious behaviors look like. To encourage reproducibility and further improvements to DeepReflect, we have open sourced our code and datasets. And with that, thank you for your attention to this presentation. I'll be happy to answer any questions you may have, and I hope you have a wonderful day.